There's a monster sleeping under Wyoming. Not a metaphorical one. A literal apocalypse-level threat that makes nuclear weapons look like firecrackers. And instead of leaving it alone like any sane civilization would, American scientists want to drill straight into it. 6 miles down, through solid rock, into a magma chamber hot enough to vaporize anything we've ever built. Why? Because apparently we learned nothing from every disaster movie ever made. Stick around, because this gets way more insane than you think. Yellowstone National Park. You know it. Geysers, bears, tourists taking selfies way too close to bison. Beautiful place. Family vacation destination. And when I say supervolcano, I don't mean big volcano. I mean a volcanic system so massive that when it eventually erupts, and it will erupt, it could end civilization as we know it. Let's put this in perspective. Mount St. Helens erupted in 1980. That explosion was equivalent to about 1,600 Hiroshima bombs. It devastated 230 square miles, killed 57 people, and sent ash across multiple states. Absolutely catastrophic by any normal measure. The last time Yellowstone erupted, 640,000 years ago, it was roughly 2,500 times more powerful than Mount St. Helens. Not twice as powerful, not 10 times. 2,500 times. The ash from that eruption covered most of North America. We're talking ash deposits found as far as the Gulf of Mexico, 6 feet deep in some places. That's not a layer of dust. That's burial. And we're standing on top of this thing right now, acting like it's just a neat place to see Old Faithful. Here's what makes Yellowstone different from regular volcanoes. They build up over time. They erupt. They look like volcanoes. Yellowstone doesn't work that way. Yellowstone is a caldera. That means the volcanic chamber is so massive that the ground above it literally collapsed inward after the last super eruption. The entire park, all 3,472 square miles, sits inside a crater from an explosion so violent it defies comprehension. Underneath that relatively peaceful surface is a magma chamber. 2 magma chambers. The upper one is about 3 to 9 miles below the surface. It's roughly 55 miles long and 20 miles wide, filled with molten rock, at temperatures exceeding 1,500 degrees Fahrenheit. Below that is an even larger chamber, extending down to about 30 miles deep. Together, these chambers contain enough magma to fill the Grand Canyon 11 times over. This isn't speculation. We know this from seismic imaging. Scientists have mapped the magma chambers by studying how earthquake waves travel through the ground. When waves hit solid rock, they move at one speed. When they hit molten rock, they slow down. By measuring these differences, researchers have created detailed 3D maps of what's underneath Yellowstone. And what they found is terrifying. The magma isn't static. It's moving, rising. The ground surface of Yellowstone has been rising and falling for decades. As magma pushes up from below, between 2004 and 2008, the ground rose about 3 inches per year. That might not sound like much until you realize we're talking about an area the size of Rhode Island lifting 3 inches annually. The amount of force required to do that is staggering. Now, before you start planning your doomsday bunker, Yellowstone isn't about to erupt tomorrow. Probably. The thing is, we don't actually know when it will erupt. The supervolcano has a cycle. It erupts roughly every 600,000 to 800,000 years. The last eruption was 640,000 years ago. So by that math, we're either overdue or we've got another 160,000 years. Nobody knows. The geological record isn't that precise. What we do know is that when it does erupt, the consequences will be global. The immediate blast zone, everything within a few hundred miles, just gone. Incinerated, buried under pyroclastic flows moving at hundreds of miles per hour. Ash would blanket the entire United States within days. 6 inches in Chicago, enough in most major cities to collapse roofs and shut down infrastructure completely. The ash would block out the sun, not for days or weeks, for years. Global temperatures would drop by 10 to 15 degrees Fahrenheit, maybe more. Crops would fail worldwide. We'd be looking at mass starvation on a scale humanity has never experienced. This isn't being dramatic. This is what the geological record tells us happened last time. And that was when there were maybe a few million humans on the entire planet. Most of them hunter-gatherers. Now we've got 8 billion people, dependent on industrial agriculture and global supply chains. So here's where it gets really interesting. Scientists have been studying Yellowstone for decades, trying to figure out if there's any way to predict when it might erupt or, even better, prevent an eruption entirely. Drill into the magma chamber, cool it down, relieve the pressure, turn a supervolcano into a giant geothermal power plant. It's brilliant. The magma chamber contains an almost unlimited amount of heat energy. If you could tap into that, you could generate enough electricity to power the entire United States several times over. And in the process, you'd be cooling the magma, reducing the risk of eruption. It's like killing two birds with one stone. Free energy and disaster prevention. What could go wrong? Well, literally everything. Let's start with the drilling. 6 miles straight down through solid rock. We've drilled that deep before in other places, so it's technically possible, but not into an active volcanic system. Regular deep drilling is already insanely difficult. The deeper you go, the hotter it gets. At 6 miles down in most places, you're looking at temperatures around 400 to 500 degrees Fahrenheit. Drill bits melt. Equipment fails. It's expensive and dangerous, but at Yellowstone, 6 miles down isn't 500 degrees. It's potentially 1,500 degrees or more because you're drilling into a magma chamber. There is no drill bit on Earth that can handle that. There is no casing pipe that won't melt. The entire concept of drilling into the magma chamber with current technology is fantasy. It can't be done. Not yet. But let's say we develop new materials. Heat-resistant ceramics, exotic alloys, whatever. Let's say we can actually drill down there. Now what? You've just punched a hole into a pressurized magma chamber. Magma exists under enormous pressure. That's why volcanoes erupt. The pressure builds until it finds a weak point and explodes outward. By drilling into it, you've potentially created the weak point. There's a real risk that drilling into the magma chamber could trigger the very eruption you're trying to prevent. The moment you breach the chamber, magma could rush up the borehole. It happened in Iceland in 2009. Scientists were drilling into volcanic rock, accidentally hit a magma chamber at about 1.5 miles down, and superheated steam shot back up the hole. They barely got the drill out in time, and that was a relatively small magma pocket. Yellowstone's chamber is thousands of times larger. The NASA scientists who proposed this idea, and yes, it was actually NASA, not geologists, they claim they can avoid this by drilling from the sides, not directly above the chamber. Come in at an angle, release pressure gradually, pump water in to cool the magma slowly, very slowly, over decades or even centuries. The problem is, we've never done anything like this before. We have no idea if it would actually work or if we'd just be creating new problems. Here's another issue. Yellowstone isn't government-owned land in the way a military base is. It's a national park, one of the most beloved national parks in the country. Millions of tourists visit every year. The idea of turning it into a massive industrial drilling operation is politically impossible. Can you imagine the outcry? Environmental groups would lose their minds. And rightfully so. The ecological impact of drilling operations on that scale would be devastating. But the scientists arguing for this plan say that the alternative, doing nothing and hoping Yellowstone doesn't erupt in our lifetime, is worse. And they have a point. If Yellowstone erupts and we had the technology to prevent it but didn't use it because we were worried about disturbing the park, future generations would consider us criminally negligent. If there are any future generations, the counter-argument is that we don't actually know if Yellowstone is going to erupt anytime soon. All the rising ground, the increased seismic activity that could be normal fluctuation. Yellowstone has been doing this for thousands of years without erupting. The magma could be moving, but that doesn't mean it's building toward an eruption. We might have hundreds of thousands of years before the next one, and this is where it gets philosophical. Is it worth potentially triggering one by trying to prevent it? What about a 10% chance? At what point does the risk of doing nothing outweigh the risk of intervention? The scientific community is massively divided on this. Some geologists think the drilling plan is insane, reckless, and based on way too many assumptions about how magma chambers actually behave. Others think it's worth exploring, at least as a theoretical option, because the potential payoff is so huge. And then there's a third group that thinks we should focus on prediction and evacuation planning, rather than trying to prevent an eruption at all. Let's talk about what monitoring currently looks like. Yellowstone is one of the most heavily monitored volcanic systems on Earth. There are seismometers everywhere, measuring tiny earthquakes, GPS stations tracking ground deformation, gas sensors measuring sulfur dioxide and carbon dioxide emissions, thermal imaging satellites, watching for heat anomalies. All of this data feeds into the Yellowstone Volcano Observatory, run jointly by the USGS, the University of Utah, and the National Park Service. They've been watching Yellowstone closely for decades. Periods of uplift when the ground rises, periods of subsidence when it falls, swarms of small earthquakes, then quiet periods. Gas emissions that increase and decrease. None of it, so far, indicates an imminent eruption. But here's the catch. We don't know what an imminent eruption would actually look like. The last supereruption was 640,000 years ago. We have no baseline for what warning signs to expect. Smaller eruptions give us some clues. Before most volcanic eruptions, there's increased earthquake activity, ground deformation, gas emissions. But a supereruption might be different. The scale is so much larger. The warning signs might be more subtle, or they might be more dramatic. We just don't know. Some scientists think we'd have decades of warning. The magma would have to rise from the lower chamber to the upper chamber, then from the upper chamber toward the surface. Unmistakable signals. Thousands of earthquakes. Dramatic ground uplift. Huge increases in gas emissions. We'd see it coming. Other scientists aren't so sure. They point to historical eruptions where the warning time was much shorter than expected. Mount Pinatubo in the Philippines gave about 2 months of warning before its massive 1991 eruption. And that wasn't even a super eruption. What if Yellowstone behaves differently? What if the warning time is measured in weeks, not decades? This uncertainty is driving the push for more research. Not necessarily drilling into the magma chamber, but better monitoring, better modeling, better understanding of how supervolcanoes actually work. The problem is funding. Studying Yellowstone is expensive, and it's hard to get funding for something that might not happen for thousands of years. Politicians aren't excited about spending billions on a threat that won't materialize in their lifetime. But here's where the geothermal energy angle becomes important. If you can frame the drilling project as an energy initiative that also happens to reduce volcanic risk, suddenly it's more palatable. You're not spending money on disaster prevention. You're building a power plant that pays for itself. Bonus. Might prevent an apocalypse. That's a much easier sell. The NASA proposal, when they floated it publicly, estimated it would cost about $3.5 billion to drill into the Yellowstone magma chamber and set up a geothermal power system. That's a lot of money, but it's also less than we spend on a single aircraft carrier. And the potential energy output would be enormous. They estimated you could generate about 10 gigawatts of electricity continuously for thousands of years. That's enough to power several million homes. The economic argument is compelling. Yellowstone could become the largest geothermal power plant in the world. It would provide clean, renewable energy with no carbon emissions. It would create jobs. It would reduce America's dependence on fossil fuels. And oh, by the way, it might also prevent a catastrophic eruption that could kill millions of people and collapse global civilization. When you frame it that way, $3.5 billion starts to sound like a bargain. But the technical challenges remain overwhelming. It's not just about drilling. Even if you successfully drill into the magma chamber without triggering an eruption, you then have to extract heat efficiently. That means circulating water through the system. Pump cold water down. It gets heated by the magma. Steam comes back up. You use the steam to drive turbines and generate electricity. Simple in theory. Nightmare in practice. The water has to circulate through rock that's partially molten. That rock is under enormous pressure. It's chemically reactive. The water isn't going to stay pure H2O. It's going to dissolve minerals, become corrosive, clog pipes, create scale buildup. Geothermal plants in other locations deal with these issues, but they're working with temperatures of a few hundred degrees, not 1,500 degrees. The chemistry at Yellowstone temperatures is completely different. Then there's the pressure management issue. As you cool the magma by extracting heat, you're changing the pressure dynamics in the chamber. Cool it too fast, and the magma could solidify in ways that increase stress in surrounding rock. That could trigger earthquakes. Cool it too slow and you're not making a meaningful dent in the eruption risk. You need to cool it at exactly the right rate. And nobody knows what that rate is because we've never done this before. There's also the question of what happens to the volcanic system long term. Yellowstone isn't just a magma chamber sitting there. It's part of a much larger geological system. There's a mantle plume underneath, a column of superheated rock rising from deep in the Earth's mantle. That plume has been feeding Yellowstone for millions of years. It's not going away. Even if you successfully cool the current magma chamber, the plume is still down there, still pumping heat into the system. Does cooling the chamber just delay an eruption? Or does it fundamentally change the system's behavior? Unknown. Some geologists argue that Yellowstone's eruption cycle might actually be necessary from a planetary perspective. Volcanic eruptions release gases from the Earth's interior. They recycle elements. They create new land. Trying to suppress Yellowstone completely might have unintended consequences we can't predict. The Earth is a complex system. You can't just remove one major component and expect everything else to stay the same. But proponents of the drilling plan say that's overthinking it. The goal isn't to shut down Yellowstone forever. It's to prevent or delay the next super eruption long enough for humanity to develop better technology or even colonize other planets. If we can push the next eruption back a few thousand years, that might be enough time for us to become a truly spacefaring civilization. Then a Yellowstone eruption, while still catastrophic, wouldn't be an extinction-level event. That's actually part of why NASA got interested in this in the first place. They're thinking about existential risks to humanity. Asteroid impacts, supervolcanoes, gamma-ray bursts, all the things that could wipe us out before we make it off this planet. Yellowstone is one of the more immediate threats on that list. And unlike asteroids, which we might be able to deflect, or gamma-ray bursts, which we can't do anything about, Yellowstone is something we might actually be able to control. Maybe. The current status of the drilling plan is that it's not happening. Not yet. There's no approved project, no funding, no timeline. It exists in research papers and theoretical proposals. They run simulations. They develop new materials that might withstand the temperatures. They model how water circulation might work. But nobody is actually drilling. Part of the reason is technological. We're not ready. Part of it is political. The public perception of drilling into a supervolcano is not great. Part of it is scientific caution. Most geologists would rather spend more time studying the system before we start poking holes in it. And part of it is financial. $3.5 billion is a lot of money for a project with no guarantee of success. But the conversation is happening. And it's happening because Yellowstone isn't going away. The magma chamber is still there, still hot, still pressurized, still capable of producing an eruption that would fundamentally alter human civilization. Every year we monitor it more closely. Every year we understand it a little better. And every year the question becomes more urgent. What are we going to do about this? There's a parallel conversation happening in the scientific community about other supervolcanoes. Yellowstone gets the most attention because it's in the United States, but it's not the only one. Tuba in Indonesia, Campi Flegrei in Italy, Topo in New Zealand. There are multiple supervolcanic systems around the world. If we develop technology to manage Yellowstone, that technology could potentially be applied elsewhere. We could be looking at a future where humanity actively manages volcanic risk on a global scale. That sounds like science fiction. But so did landing on the moon before we did it. So did splitting the atom. So did most of the technology we take for granted today. The question isn't whether it's possible to drill into Yellowstone and extract energy while reducing eruption risk. The question is whether we can do it safely and whether we should try. The ethical dimension is fascinating. Do we have a responsibility to future generations to prevent a supervolcanic eruption if we can? Or do we have a responsibility to not mess with natural systems we don't fully understand? Both arguments have merit. The precautionary principle says don't intervene in complex systems until you're sure of the consequences. But the existential risk principle says when facing potential extinction, you take calculated risks to prevent it. One thing is certain. We're not ignoring Yellowstone anymore. 50 years ago, most people didn't even know it was a supervolcano. Now it's common knowledge. We're monitoring it constantly. We're developing contingency plans for what to do if it shows signs of erupting. We're researching potential interventions. Whether we actually drill into it or not, we're taking the threat seriously. And maybe that's the real story here. Not that Americans are recklessly drilling into a volcano, because we're not. Not yet. But that we're finally confronting the reality that our planet has these enormous geological forces that could destroy us. And we're starting to ask whether we have the capability and the right to control them. It's hubris, maybe. But it's also survival instinct. And it's definitely one of the most ambitious things our species has ever considered attempting. The next few decades will be telling. As technology improves, as our understanding of Yellowstone deepens, the drilling proposal will either move forward or be permanently shelved. Either way, we're living in a unique moment in human history. The moment where we transition from being at the mercy of nature to potentially being able to manage planetary-scale geological systems. Whether that's brilliant or insane, we'll find out soon enough. Thanks for watching. Hit subscribe if you want more videos about humanity's questionable decisions. And if you've got thoughts about drilling into supervolcanoes, drop them in the comments. I'm genuinely curious what people think about this.